Ladies and gentlemen, today our group is presenting on our project on implementing a part of speed POS data using hidden Markov models. And from introducing the problem to the introduction and problem, certainly in the theoretical background, 30 implementation details, challenge and result, and the last one is demonstration and conclusion. Now, let's talk about the core problem. What is POS tagging? POS tagging or part of speed tagging is the process of automatically assigning grammatical categories to each word in a sentence, such as noun, verb, adjective, and so on. We have an example in here. In a sentence, the quick brown fox jumps over the lady dog. We might take it as the is the determiner, which is adjective, brown is adjective, fox is noun, jump is verb, and so forth. So why is this important? This is the first known step for many natural language processing, graphical NLP tasks like voice translation, question answering, or sentiment analysis. Because it has computer understand the grammatical structure of sentences, making language processing more effective. For a solution, we choose a Markov model because they are built powerful, probabilistic model that will suit for frequent data like sentences. The core idea of AIN is that hidden stepes, in this case, the POS chart generated observable events, which are the actual words. This model allows us to predict the optimal task sequence based on probabilities, and we reveal what we are going to calculate. Now, let's get into the theoretical background. About this section, I will explain the theoretical variation behind our implementation. Firstly, what is a hidden Markov model? An AIN is a probabilistic model used to describe random processes where the true status, hidden status aren't directly observable. Not only true observation in our field of carrying out the hidden status of POS apps right now over the observation the most uh, in the and the model relies on probability to connect them. The element is trained using maximum likelihood estimation, which means we calculate the probability directly from the training data to make the model fit the observed data as well as possible. Specifically, FM has three main types of probabilities. Initial probability. In the first one, this is a probability of the first period tag in a sentence denoted as in the slide. You can see, for example, sentences often start with a noun more frequently than a verb. Secondly, it's a transition probability. This is the probability of moving from one period tag to the next. For instance, after a noun, the chance of the verb appearing might be higher than another noun, reflecting grammatical rules. And the last one is emission probability. It's a probability that a given director produces a specific word. For example, the word run is more than another verb up than a noun. And this probability was computed with the training data and found the basis for creating the optimal task sequence for the new sentence. Next, we will cover the implementation details. Okay, the next one I will define visual rhythm.
Okay, so I'm going to talk about the implementation details. So first, the decoding problem. So why do we need a special algorithm? So first I want to talk about the decoding problem first. We have to find the most likely POS tag sequence for a new sentence. So from the HMM Ming had just present, we have initial probability, transition probability and emission probability. So the task here, we have to determine the most probable hidden state sequence. So we'll talk about why we use Viberry algorithm here. So imagine a short sentence which is 5 words, and say we have about like 10 tags. So the total number of sequences, possible tag sequence is 10 power 5, which is around like 100,000 sequences. It's kind of too long, too many possibility that it would be too slow. So in the Viberry, we will use the dynamic programming technique, which is we find the best path to current tag comes from the best path to the previous tag. So it will efficiently find the most probable tag sequence. So next we will talk about the Viberry in practice. So here we have the Viberry matrix and back-pointed table. The Viberry matrix will store max probability of each tag at each word, and the back-pointed table will store previous tag, leading to the max probability. Okay, so we will use log probability to avoid underflow tools, and I will talk about it more in the demonstration section. Okay, so next here we have the Viberry step. So I will talk briefly about that. We have 3 main steps to running Viberry on a sentence. Yeah. The first is initialization. Initialization, for the first word, we calculate the probability of each tag starting up from the sentence, multiplied by the probability of that tag, generating the first word. Like you can see the initialization here is B of T1, multiply the B of word on, like with the condition of T1 for each tag of the first word. The next is a recursion. So for every subsequent word, we check all possible previous tags, find the path that give the highest total probability, and store the result. And the last one is the termination and backtrace. When we reach the last word, we find the best tag in the final column. Then we follow back pointers step by step all the way back to the first word. This backward path gives us the final optimal sequence of the tag for the entire sentence. Okay, so I will talk briefly about the example here. So you can see the word list here. We have time and fly. Here is the sentence time flies. We have tokenized the sentence. So we will start from the first step is the initialization. So the first word fly here, a first word is the time. Viberry calculates the starting score for every possible tag. This score combines the initial probability and the emission probability for time, and it will lead to the tag now. As you can see in the first table here, the now is like bold with minus 0.3, which is the highest.
My name is Hòa and I will introduce the next sessions. However, when we apply this post-tagging to real language data, we also encounter practical challenges such as unknown word problem that affect performance. In the next sessions, I will discuss these difficulties and how we evaluate our model. For example, in the sentence quokka run quickly in the forest, the word quokka was unseen in our training data. So the emissions probability pivot tag would be 0 without any handling mechanism. The model cannot assign a tag correctly to that word, which can lead to inaccurate tagging for the rest of the sentence. To address this issue, we apply a couple of simple but effective strategies. First, we use a backup approach where we assign probabilities beyond the overall frequency of each tag in the training set. For example, if most of the words in the training data are tagged as now, the model might guess that an unknown word like quokka is a noun. Second, we assign a small fixed probability to unknown words, so the model can still make a reasonable prediction. For example, for a newly corn was like progenified rather than having zero probability, it receives a tiny non-zero probability, allowing the model to proceed. Let's talk about evaluation method. We use tagging accuracy to measure how well the model performs. This metric is defined as accuracy equal correct tag divide total text. Accuracy is calculated on the test set that the model has never seen before, so it reflects the model ability to generate two new data. For example, on a sentence like the quokka run quickly in the forest, our model correctly tests quokka as a noun and runs as a verb, showing that it can generate beyond the training vocabulary. To be more detailed, let my partner Duy show our demonstration.
I'm gonna be responsible for the demonstration part. So first we have to load and pre-process the brown corpus dataset from NLTK. So just a small notice here, I will show the code later. I mean, show the code on Google Colab, and I will just talk briefly about the code. Okay, first here is load and pre-process the brown corpus dataset from NLTK. You can see the code here is loaded successfully. Like you have just call nltk.download brown and download universal tag set. We have to import the corpus and dividing train test data ratio to 80 and 20. So the next step is to estimate transition probability is tag to tag and admission probability is tag to word from the training data. So the tag count data will look like the array the dictionary I put below here is now is 27,000 or verb is 18,000. It's just sample data. Here is the function signatures for estimate HMM parameters, and we also have in the function we have the transition prob and emission prob, and I will just put the sample data here, and here is the result of the code. We would here is the implementation of Vibrity algorithm to find the most likely POS tag sequence for test sentence. I would run in the test sentence data later. Here is the evaluation and the final result. And now I will show the code. Okay, so here is the code demonstration for that. So first we have to implement the load and process the brown corpus dataset from MLTK. It will take a lot of time to load it, not really. Okay, so here we have the total sentence loaded is 57,000. And here we have to train and test split the corpus. Here you can see the split ratio is 0.8 here. So we have about like 80% for training and 20% for testing. Let's just run it and see the result. Okay, here you can see the training sentence and testing sentence is splitted. And we will calculate the unique tags is about 12, and the vocabulary size of this corpus is about 45,000. Up next is HMM parameter estimation. Okay, so Ming has already explained this, so I will just show you the code. We will run it here. Here you can see the tag count, like how many, the tag count here is represented in the counter. And the HMM parameter estimated has been initialized. And we will move to the part we will run the Vibrity algorithm. Okay, here, so let's just run the code. Nothing happened because I haven't called the code yet. And you can see briefly the get emission prop is just like the helper function. And the two most important thing here is the Vibrity table or Vibrity matrix to store the max log probability for any path ending the word I with tag, and the back pointer for the road back tracing. Okay, so the handling unknown words here. We run on the here I talk about the running on the test data. So we will leave for each sentence in the test data. With the word and true tag here, it's just like we tokenize the word since it is in English. So tokenize the word, each word is just like space, one space, each word. So it's pretty easy to split them. Let's just run it. And nothing happened because we haven't called it yet. And we will calculate all these things under this execution part. And you will see the calculating accuracy on the test set. And we have the total test is 181,000, and the correctly predicted tag is about 173,000, and the tagging accuracy is about like 0.95. It's about 95%. I think it's a pretty great rate. Okay, so my part here is done, and
Okay, that's our demonstrations presented by my partner Duy, and you can see that we successfully built a functioning HMM post tagger, and the model learned from training data and generalize well to unseen text. And our approach is a probabilistic model and efficient decoding. And the last one is accuracy, so the model effectively capture grammatical structure. And thank you for listening our project.